so that those that are not able to be in the live class, or those that want to watch the class after the lectures, can go on the LMS and watch it via the link that will be provided. So because for now, we will only have the maximum that Zoom can take. Other people may not be able to join. We are so sorry for this, because by Wednesday, we're going to have more links, and the three of us will be teaching simultaneously to our respective classes. I guess we can't have more than 300, because we can see just 300 participants here. So for Physical Chemistry 1, we have three of us that will be taking the class. Professor Isambo, I am Dr. Olusheyi, and also Dr. Agumbiade. So the three of us will be taking this class for Physical Chemistry 1. So what is going to happen is that in the next, before the end of today, you all will be grouped into 3 different groups, and you will be clicking the link of the lecturer that will take your group. For example, I'll be taking the medical students. Dr. Agumbiade will be taking chemistry and biological sciences, where Professor Isambo will be taking another group of students. All this information will be on your LMS, and you will have your respective links to join. As you can see, we are 300 in this Zoom now, and we are over 1,500 students. So, but don't worry, the link, the recording of today's class will be made available on LMS for those that are not allowed to join the live class. Subsequently, we'll make rooms for more students to join. So we'll continue, start with the class right away. So we are continuing with the lectures, and for Physical Chemistry 1, we are starting with chemical bonding. Today's class is centered on chemical bonding. I am sure that many of you have done chemical bonding in your undergrad, in your secondary school. So this is not a strange thing to you. Chemical bonding is all what you know from. So this is going to be a revision, and a little will just be added for you to top up your knowledge of chemical bonding. So we're starting right away with electrovalent and ionic bonding. So I don't want to waste our time. I would have loved you all to define what we mean by this. I would have loved you to define that, but we know we're so many, but I know that, so we just teach and you will follow the class. So now, chemical bonding, we know that we have atoms, and atoms come together to form molecules. And these atoms that they come together, there's an attractive force that keeps atoms in any compound together. Let's say, for example, you have sodium chloride, NaCl. We have sodium and chlorine. Sodium is an atom, chlorine is another atom. But when they come together from individual atoms to make up a compound, there is a force of attraction that is holding sodium atom together with chlorine atom. So that chemical force, an attractive force that keeps atoms together in any molecule, that will not make sodium to go a separate way and chlorine a separate way in sodium chloride, is called chemical bonding. So this chemical bonding is a phenomenon whereby chemical substances are held together by attraction of atoms to each other. So atom A and atom B are linked together by a chemical bond, and this linking of chemical bond can be either through sharing or exchanging of electrons by electrostatic forces. I will take that again. The chemical attractive force that holds atoms together in molecule is as a result of electrostatic forces that either shares, the electrons are shared by these forces, or the electrons are exchanged. And when this happens, there will be a strong force that will hold the atoms together in a molecule. And it doesn't have to be just 2 atoms. You could have, let's say, H2SO4. You have 2 atoms of hydrogen, 1 atom of sodium, of sulfur, and 4 atoms of oxygen. All these atoms are held together in H2SO4 by what we call chemical bonding. Now, to understand what we mean by chemical bonding, there are 2 concepts that you have to know. The first one is valence electrons, and the other one is the octet rule. valence electrons, and octet rule. These are the two key concepts that will help our understanding of chemical bonding, whether the electrons are transferred from one atom to the other, or the electrons are shared between atoms in a molecule. So now let's start with the valence electrons. What are these valence electrons? We know that we have already established that before any bond can be formed, what makes this bond possible are what we call electrons. Electrons are either transferred or shared. And when they are transferred or shared between atoms, you have what is called a bond, or maybe double bond or triple bond, as the case may be. But in every atom, it's not all the electrons in an atom that participates in bonding. You know that atoms are made up of, you have protons, neutrons, and electrons. And the electrons are usually the number of, your atomic number is the number of protons and or electrons. So, but not all these electrons in an atom, in a given atom, will participate in bonding. The only electrons that are able to participate in bonding are what we call the valence electrons. So what are these valence electrons? The valence electrons are the electrons that reside in the outermost shell of an atom. You know that there are electrons that are localized around the nucleus of an atom, and these electrons reside in different shells. So we have different orbitals and shells. So the outermost shell, the electrons that reside there are called the valence electrons. And these electrons are usually found either on the S or P subshells. For example, you have sodium. The total number of electrons in sodium atoms are 11. You have 11 electrons in sodium. But you know that all the 11 electrons do not reside on the outermost shell. If you look at the electronic configuration of sodium, you have 2, 8, 1. Remember, the first shell has 2 electrons. The second shell has a maximum of 8 electrons. And the third one, now the 11th electron now will be on the third shell. So for sodium, sodium has 1 valence electron. For sodium to participate or to form a bond with any other atom, the only available electron will be the 1 valence electron on the outermost shell. The remaining 10 electrons will be held in place, and the 11th electron, which is the valence electron, will be the one that will participate in bonding. So let's look at some other examples. You have a knowledge of electronic configuration. You have the first shell has just the s orbital. The second shell has s and p orbitals, and you have 2s and 2p. And you know that the maximum number of electrons for the s orbital is 2. Then the p orbital has 6 electrons. Samuel Ekoja, you have a question? So let me see, you've raised your hand. So you can unmute yourself, Samuel Ekoja, to ask a question. Samuel Ekoja.
That was a mistake, ma.
Okay. So now you can see that from your basic knowledge of chemistry, the s orbital has maximum of 2 electrons. The p orbital has a maximum of 6 electrons, and the d orbital has a maximum of 10 electrons. And these orbitals are arranged in shells. So you have the first shell where you have your 1s, then the second shell you have the 2s and the 2p, and has a total of 8 electrons. So let's see for carbon now. Carbon has an atomic number of 6, meaning that there are 6 electrons in total for carbon atom. And if you look at the distribution of the electrons, you have 2 electrons in the 1s orbital, 2 in 2s orbitals, and the remaining 2 in the 2p orbitals. So for carbon now, the second shell, the outermost shell has 4 electrons. In the valence electrons are 4. Let's look at oxygen. Oxygen has 8 electrons in total. The first shell has 2 electrons, and the second shell has a total of 6 electrons. So oxygen has 6 valence electrons. They're looking at sodium. Sodium has 2 electrons in the first shell, 8 electrons in the second shell. So you can see that for sodium, the second shell is filled up completely with 8 electrons. That's the maximum. Then the third shell now has 1 electron in the s orbital. So for sodium, it has 1 valence electron. So looking at this now, you can see the number of electrons in the valence shell. Now we can use the electron dot structure to designate the number of valence electrons. Looking at carbon now, you see that the 4 valence electrons are seen with 4 dots surrounding carbon atom. For oxygen, the 6 valence electrons are shown, the 6 dots surrounding the oxygen atom. Then for sodium, the 1 valence electron is just 1 red dot as the valence electron. So what we do is that we use what we call the Lewis symbol to designate the number of valence electrons. And I will give you an example. You do a quick walk in your notebook, write all the elements and begin to put a dot of the number of valence electrons that they have. I've done one as an example for the first row of the periodic table, where we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And you can see a progression. Lithium has 3 atomic number of 3. And for the 3 electrons, the first 2 electrons of lithium are in the first shell, 1s2. So the third electron of lithium is the only valence electron, and you see 1 dot for lithium. Beryllium has 4 electrons, 2 are in the first shell, 1s2. So the remaining 2, you can see 2 dots on beryllium. Boron similarly has 3 valence electrons. The remaining 2 of the 5 electrons are in the first shell. Carbon has been done previously for us. The 4 valence electrons, you see them surrounding them. And when you are placing these valence electrons, you don't pair them up. You start putting them singly before you pair up. Coming to nitrogen now, nitrogen has 7 electrons. 2 electrons are in the inner shell, the first shell, and the 5 electrons, you can see them surrounding nitrogen. So these are the 5 valence electrons for nitrogen. You first place them singly before you pair up. So there are 2 of them are paired, while the other 3 are held singly. Moving to oxygen, oxygen has 6 valence electrons, and you can see also 2 are paired and the other 2 are unpaired. So you have 2 pairs of 4 electrons and the other 2 are singly held. Fluorine has 7 valence electrons and neon has 8 valence electrons. So you can do it for all the atoms on the periodic table based on the total number of electrons, and you can arrange them in shells. So what we are interested in, according to the Lewis symbol, is just the valence electrons, and as you can see them arranged. Another striking thing you also see with this number of valence electrons is that it also gives us an idea of the groups where the atoms belong on the periodic table. For example, lithium has 1 valence electron and lithium belongs to group 1. Beryllium has 2 valence electrons and it belongs to group 2. Nitrogen has 5 valence electrons and belongs to group 5. Neon has 8 valence electrons and it belongs to group 8. So you can see that once you know the atomic number, you know the total number of electrons, you can arrange the valence electrons, and that will give you an idea of the group that they belong to on the periodic table. So this is the periodic table, as you can see. And the periodic table, like I said before, gives an idea of the number of valence electrons. See, lithium now has 1 valence electron in the second shell. Sodium has 1 valence electron in the third shell. Potassium has 1 valence electron in the fourth shell. And you can see for others, the number of valence electrons are seen. You see boron now has 3 electrons distributed between the s and p orbitals, 2 in the s orbital, 1 in the p orbital, and that is 3. That's why boron is in group 3. If we look at nitrogen, has 5 valence electrons. Of these 7 electrons, 5 of them are in the valence, the outermost shell. So these 5 electrons make nitrogen to be in group 5. Similarly for phosphorus is in group 5. Arsenic is in group, phosphorus and nitrogen are in group 5. Looking at oxygen and sulfur as well, they are also in group 6 because they have 6 valence electrons. If you look at fluorine and chlorine, they have 7 valence electrons. And the inert gases or the noble gases, they always have filled valence shell. Their outermost shell is always filled. For example, for helium, helium has 2 valence, has 2 electrons, and the 2 electrons completely fill the first orbit, the first shell, the s orbital of the first shell. And you can see these 2 electrons completely fill the s. That's the maximum number of electrons the s orbital can have in the first shell. By the time you get to neon, the 10 electrons are distributed between the 2 shells. The first shell has 2 electrons, the remaining 8 electrons are in the second shell, and the maximum number of electrons for the second shell is 8. And that is why you will see them having 8 valence electrons. Similarly, for argon, you see the 8 valence electrons. So for rare gases or the noble gases, their outermost shell is filled up. It has the maximum number of electrons it can take. So that is why they are unreactive, because the shell is completely filled up. It cannot collect more electrons, neither can it donate 1 electron, because once the shell is filled up, the atom attains a level of stability. And once they are stable with their filled shell, they can neither take extra electrons nor donate an extra electron. And that is why we call them inert gases, because they don't take part in chemical reactions. So we'll only be focusing on group 1, group 2, group 3, group 4, group 5, group 6, and group 7. So now we want to look at some key things about this group. Let's look at group 1 and group 2. Remember, for group 1 and group 2, group 1 have 1 valence electron, and group 2 has 2 valence electrons. So what is the general thing for them? We'll take 2 examples of members of groups 1 and group 2. We'll take an example of sodium as a member of group 1. You know that sodium has 11 electrons, like we said, of which 1 of the electron is on the valence shell, the outermost shell. If you look at it now, the first shell has 2 electrons, the second shell has 8 electrons, and the 11th electron, as you can see, is on the valence shell. We're not interested with the filled orbitals, we are only interested in the valence shell. And that is why you can see only 1 electron on the outermost shell. Going to magnesium in group 2, magnesium has 12 total electrons, and the 2 first shells are filled up, and the last shell, the third shell, has 2 electrons in the valence orbital. So on the valence shell, so you can see that sodium has 1 valence electron, magnesium has 2 valence electrons. Going back to our table, you see sodium is in group 1, 1 valence electron, while magnesium has 2 valence electrons. So now these 2 electrons, this 1 electron here can be easily given up. It can be donated, because it's for a shell to be stable, it must have 8 electrons, and sodium has 1. You need 7 electrons to make a filled orbital or a filled shell. So sodium will readily give that 1 and donate it. Similarly for magnesium to be stable and happy, it needs 8 electrons in its outermost shell. Remember, our valence electrons, our inert gases have 8 electrons, and they are happy, they are stable. So for sodium to be happy, it will need to release this 1. For magnesium also to be stable and happy, it will release these 2 valence electrons. So that is why we call them electropositive elements, because they can give 1 electron away or give 2 electrons away, and they become positively charged. We'll look at that later. So groups 1 and 2 elements, they always like to give up their valence electrons. Remember, only the valence electrons are given up. They give them out, so that when sodium gives this 1 out, the 2 shells will be completely filled. When magnesium gives out these 2 electrons, these valence electrons, the 2 filled shells will be completely filled. Now let's jump to group 6 and group 7 elements. The group 6 and group 7 elements, you see oxygen has how many valence electrons? 1, 2, 3, 4, 5, 6. You need just 2 electrons to be happy and have a complete shell. So what will oxygen do? Oxygen will be looking for who to donate and give it 2 electrons, so that the third shell will be, the second shell will be filled up and oxygen will be happy with 8 valence electrons. Similarly for fluorine, fluorine has 9 total electrons, of which 2 are in the first shell and the remaining 7 are in the outermost shell. So fluorine needs just 1 electron to be happy and make a complete shell. So these 2 atoms, and they are representative of group 6 and group 7 elements. Group 6 elements are busy looking for 2 missing electrons to complete their octet, while a fluorine also is looking for 1 electron to make it 8 valence electrons. So these atoms, they are called electronegative atoms. What are they looking for? They are looking for atoms that will donate electrons for them to make their shell filled up. So this, what do we need to know about these valence electrons? So the valence electrons, the representative elements in the same group of the periodic table, have the same number of valence electrons. So let's go back to our periodic table. If you go here now, in group 1, all of them have 1 valence electrons. If you go to group 2, they all have 2 valence electrons. If you go to group 3, you see 3 valence electrons. You go to group 4, 4 electrons, group 5, 5 electrons, group 6, 6 electrons, group 7, 7 electrons, group 8, 8 valence electrons. So how do you know which elements of the same group? They will all have the same the same number of valence electrons in their s and p orbitals. So the number of valence electrons for the elements is the same as the group number. So aluminum has 3 valence electrons, it belongs to group 3. Fluorine has 7 valence electrons, and on the periodic table, it belongs to group 7. But for each group or each shell, the maximum number of valence electrons is 8. So once the shell is filled up with 8 electrons, that shell is completely filled. And that leads us to what we call the octet rule. Electrons are arranged with the 8 valence electrons. So, and that, 8 is opt from the 8. So the octet is from this 8. So any electron that has 8 valence electron will be stable. And that is why any atom that has 8 valence electron will be stable. And if you look at the periodic table that we saw before, all these elements that have 8 valence electrons are stable, with the exception of helium. Helium cannot make an octet because it has just 2 electrons in the atom, and helium will form a duplet. Helium will form a duplet, while neon and argon will form octets. So the 8 electrons, any element that has 8 electrons would be in the valence electron will be stable. So the valence electron configuration of noble gases are considered the most stable. And as you can see, they all have 8 valence electrons and they are stable, except helium that has 2. And that is why they are called inert gases, because they don't partake in any chemical reaction. So all noble gases have their outermost s and p subshells completely filled up. So the octet rule tells us that the noble gases are the most unreactive of all elements. And the reason given for this is that their valence shell is completely filled. They are not looking for electrons to complete an octet. They are not looking for, they are not aspiring to donate electrons so that they become octets. They are just happy with their 8 valence electrons. So atoms of many elements also desire to acquire this valence electron states. So they always want to also, okay, they want to be like this noble gases that have 8 electrons. So they are looking for a way they too also will have their valence shell having 8 electrons. And in doing so, they can lose their electrons or gain electrons or share electrons to produce an octet configuration. And going back to our sodium now, sodium would rather lose this one electron so that the next shell will be completely filled up. Magnesium also would rather lose these two electrons so that the next shell afterwards will be filled, because what they want to is what they are attaining is an octet. Similarly, oxygen would, it's difficult to lose 6. It's easier for oxygen to gain 2 more to fill this shell. And also for fluorine or group 7 elements, it's easy for them to gain 1 electron to fill the octet. So every element, they are always tending towards gaining electron, like chlorine and oxygen, group 6 and group 7. They want to gain either 1 or 2 electrons, or lose electrons like groups 1 and 2 elements, or share electrons like your group 3, 4, 5 elements. And when they are trying to do this, they'll be forming compounds. So now in a way to gain electron or lose electrons, they form compounds by reacting with other atoms. And this tendency is known as the octet rule. So going forward, you see that elements would rather gain electron or lose electron, gain electrons, or share electrons. When elements come together to share themselves, they will they either gain, lose, or share electrons. That is what they do. That is their aim. They want to either gain electron, lose electron, or share electron. And the only reason why they do this is because they want to attain stable electron configuration. And the electron configuration they want to attain will be such that it's similar to the next higher or lower noble gas in the periodic table. Let's quickly go back to that periodic table. So for example, when lithium loses this 1 electron, what do you think will be the configuration? The configuration will be similar to that of helium. It has 3 electrons. If it loses 1, you have 2 electrons, and that 2 electron will be similar to helium, which is the noble gas preceding it. Similarly for sodium, sodium has 1 electron in the valence shell. If it loses this 1 electron, instead of having 1s2, 281, it becomes 28, and that 28 will be similar to that of neon, the preceding noble gas. Look at fluorine, for example. Fluorine needs just 1 electron to complete an octet. And when fluorine collects that 1 electron, it will be similar to that of neon that has a configuration of 2 8s. So that means that fluorine will gain 1 more electron. It comes from 9 electrons. Fluorine will become 10 electrons, and it will be similar to neon. When chlorine also gains 1 electron, it becomes 18 and it will be similar to argon. So when they gain electron or lose electron, they always attain the configuration of the next higher or lower noble gas that is in the preceding or coming after them in the periodic table. And this idea forms the basis of what we call the electronic theory of bonding, when they lose electron or gain electron. So every atom on the periodic table, they are neutral by default. Your sodium has 11 electrons, is neutral. Potassium has 19 electrons, and that's a neutral atom. And calcium has 20 electrons, that's a neutral atom. But by the time they lose electrons or gain electrons, they become ions. So for example, your groups 1 and group 2 elements, is easy for them to lose electrons. And when they lose electrons, they become positively charged and they become cations. So they are called cations when they lose electron. So when sodium loses that valence electron, it ceases to become Na, it now becomes Na plus. That plus tells us that it has lost 1 electron, is electropositive. Then for the anions, when they gain electron, for example, when fluorine gains 1 electron, remember fluorine has 7 valence electrons. If it gains 1 electron, it becomes an anion, and it is electronegative. So groups 1 and group 2 elements are termed electropositive elements because they gain electron. Group 1 will get, they lose electrons, sorry. Group 1 will lose 1 electron to become positively charged. Group 2 atoms will lose 2 electrons to become positively charged. Now put 2 plus. For example, magnesium will lose 2 electrons, becomes Mg2 plus. Sodium will lose 1 electron, becomes Na plus. Therefore, the anions, oxygen can gain 2 electrons, and that is electronegative, and that will be O2 minus. The 2 minus means that it has gained 2 electrons. So fluorine can gain 1 electron because it's in group 7 to form an octet, and it becomes F minus. So let's look at the groups for the electropositive elements on the periodic table. Atoms that belong to the first three groups, group 1, group 2, group 3, they lose electrons from their outermost shell. Remember that the only electrons they can lose are the valence electrons residing at the outermost shell. So they will lose these valence electrons, and in losing the valence electrons, they become positively charged. And when they become positively charged, the number of the charge they have, number of charge they carry is determined by the number of electrons they lose. Now, let's take an example that we have been talking about, sodium. And incidentally, they are majorly metals. So they donate electrons to form positive ions. Let's look at the first group, sodium. Sodium has 11 electrons, and the structure is 281. So you can see that it has 1 valence electron, 1 electron in the outermost shell, which is easy for sodium to give out. Because when sodium gives out that 1 electron, it can now have these 2 8. So when sodium takes away this 1 electron, it becomes Na plus. This 1 positive sign shows that it had lost 1 electron. So the ion will no longer be 281, it will be 28. And you can see that the outermost shell is now an octet, and it is now similar to neon, which is the previous noble gas. Let's go to magnesium. Magnesium has 12 atomic number of 12, meaning that it has 12 electrons, and the configuration is 282, meaning that it has 2 valence electrons in the outermost shell. And it's easy for sodium and magnesium to lose these 2 electrons, and magnesium now no longer is neutral, it becomes a cation, Mg2 plus. So this 2 plus indicates that magnesium has lost 2 valence electrons to attain the configuration of neon, the previous noble gas. Similarly, aluminum, a metal also, can lose the 3 valence electrons to become Al3 plus, and the structure of the ion will be 2,8, just like neon, the previous noble gas. So you can see now that the trend for group 1, group 2, and group 3 elements is that they would have the number of electrons they lose will correspond to the number of charges they will carry on their ionic species they form. So the ionization energy has a role to play, because you know the ionization energy is the amount of energy that is required to remove the highest energy electron from an isolated neutral atom in the gaseous state. That is what the ionization energy is called, is defined as. So for groups 1 and groups 2 elements, the ionization energy is always positive, because energy is added to remove an electron. You are removing an electron from helium, from lithium, for example, and sodium and potassium. So energy energy must be added to remove that electron. And you can see for the metals like lithium and beryllium, sodium and magnesium, potassium and calcium, they have low ionization energy. They have low ionization energy, while the non-metals have very high electron ionization energy. You can see the trend now. The ionization energy increases from metals, and as you go increase in the period, across the period, ionization energy increases. So the ease of removing electron from the highest energy orbital in an acylated neutral atom. So for metals, you can see it is low. And as the atomic number increases, the ionization energy, you can see the trend. So now we've seen how anions are formed. Let's look at how cations are formed. Cations are formed majorly by elements in group 6 and 7. Remember, group 6 elements have 6 valence electrons. Group 7 elements have 7 valence electrons. So for sulfur, which is a representative of group 6 elements, the configuration is you have 16 electrons arranged as 2, 8, 6. So you have 6 valence electrons, and it's not easy to lose 6 electrons. It is not easy at all. So it is easier for sulfur to gain 2 electrons, so that for sulfur to be happy and become an octet, it needs 2 electrons. So sulfur would rather look for any atom to donate 2 electrons. And when 2 electrons are donated, sulfur is now electronegative, carrying -2 charge. And when that happens, the configuration now becomes 2, 8, 8, similar to the next noble gas, which is argon. Let's look at chlorine. Chlorine has 17 atomic mass. That means it has 17 electrons, of which 7 are valence electrons. So the 7 electrons residing in the atomos shell, so chlorine in the neutral state is not happy because it wants to be an octet, and it's easy for it to gain 1 electron. Look for any atom that can donate 1 electron. And when 1 electron is collected, the configuration of the atomos shell becomes that of an octet. So you can now see chlorine now behaves like argon, having 8 valence electron, 2, 8, 8. So the number of electrons that are gained by electronegative elements will be determined by the number of charges they carry. Chlorine, fluorine, iodine, they will gain 1 electron, so they will have 1 negative charge. Sulfur and oxygen will gain 2 electrons, and they will have 2 negative charges. So now electron affinity is what takes place that is more significant for electronegative elements. And what is electron affinity? Is the energy that is released when an electron is added to an isolated atom in the gaseous state. It's different from ionization energy for groups 1, 2, and 3, which is the energy that is gained when an electron is removed from an atom in the gaseous state. But electron affinity is the energy change that occurs when an electron is added. So, and electron affinities are usually negative because energy is released when a neutral atom adds an electron to it. As you can see how high it is. Fluorine, chlorine, bromine, iodine, they have a very high electron affinity, followed by the next compound, your nitrogen. You have oxygen, and the group 6 elements. The group 6 elements follow, then group 5 elements. I can see for the groups 1, 2, and 3, they don't have electron affinity because they are losing electrons. So for metals, electron affinity is very low, while for non-metals, your group 6 and 7 elements, the electron affinity is very, very high. So we've looked at groups 1, group 2, group 3, they're electropositive. They become electropositive by losing their electrons to form an octet. Group 6, and 7, they are electronegative. They gain electrons to form octets. Now, groups 4 and group 5, they are in between. So they attain the electronic structure similar to noble gases. They don't lose electrons. They don't gain electrons. They share electrons. So they share electrons with other atoms. And so they don't do electron transfer, either gaining or losing. They share with other atoms to form their bond. So when these electrons are lost or gained, a bond will be formed between who is gaining and who is losing. And when electrons are shared also, a bond will be formed by the elements or atoms that are sharing their valence electrons. One key thing you need to know that these electrons that are transferred or shared are only valence electrons. Any other electrons that are not in the valence shell remain intact. So bonding only involves valence shells or electrons that reside in the valence shell. Now let's go to how this now takes place. The sharing of the transfer of electron, either by losing or gaining of electron. How does this happen? So we're starting with what we call the electrovalent bond or ionic bond. An ionic or electrovalent bond is a bond formed between metals when metals and non-metals react. And remember that your metals will transfer electrons, they will lose their electrons to form an octet, while your non-metals will gain electrons to form an octet. So when this happens, group 1 or group 2 will transfer electrons to the non-metals who want to collect electrons in group 6 and group 7. And when this occurs, the electrons are transferred from the metal to the non-metal, such that the outermost shell of the metal will attain the configuration of a noble gas, and the outermost shell of the non-metal would also attain the configuration of the noble gas. Let's look at this example between sodium and chlorine. Sodium is in group 1, as you can see the Lewis structure, having just 1 valence electron. Chlorine has 7 valence electron because it belongs to group 7. So now it's easy for chlorine to say, I need to throw away this 1 electron so that I'll be happy and become an octet. Then chlorine say, oh, how I wish I have just 1 more electron to fill up this my valence shell, and I'll be happy as I become an octet. So sodium say, okay, I have 1 extra, let me give you. So sodium, this valence electron is now transferred from sodium to chlorine. Valence electron is transferred from sodium to chlorine. And when this happens, remember that sodium had 11 electrons, 11 protons originally. So 1 electron leaves, nothing happens to the proton, is the electron that leaves. And originally, chlorine had 17 electrons. So when it gains 1 more, it becomes 20 electrons. And this is now what happens. This 1 electron is transferred here. So sodium now becomes positively charged, as you can see, and chlorine becomes negatively charged, as you can see. So these are the ionic species. So if you now count sodium, it has 1, 2, 3, 4, 5, 6, 7, 8. And the 2 in first shell. So this is happy. Chlorine also has 1, 2, 3, 4, 5, 6, 7, 8. So the 2 of them are now become octets, and they are happy with their valence shells. So they are formed between metals and non-metals. So ionic or electrovalent covalent electrovalent are formed between metals and non-metals through electrostatic attraction. So let's look at the Lewis structure. Remember, the Lewis structure is just the dots of the number of valence electrons. Just put 1 dot by the side of sodium to show 1 valence electron, 7 dots in pairs to show the 7 valence electrons of chlorine. So this 1 electron comes there, sodium becomes positively charged, and chlorine becomes negatively charged. And that is how you have your NaCl. Let's look at another example between calcium and chlorine. Calcium is in group 2, has 2 valence electrons. Chlorine is in group 7, has 7 valence electrons. So calcium has 2 electrons to give away. Chlorine only needs 1. So 1 electron goes to chlorine. Chlorine is happy. But calcium is still having 1 electron. Calcium be like, what do? I still have 1 extra electron. So chlorine will say, oh, I have another friend that can come to collect 1 more electron. So chlorine beckons to another chlorine sister atom who also needs 1 electron to collect the 2nd electron of calcium. So looking at this now, calcium is able to share the 2 valence electrons or transfer the 2 valence electrons to 2 chlorine atoms. And by so doing, when calcium loses the 2 valence electrons, it becomes Ca2+, and each chlorine atom collects 1 of the valence electrons to become chlorine negative, and the formula of the compound will now be CaCl2, 2 atoms of chlorine that collected 1 electron each from the valence shell of calcium. So we talked before about ionization energy, that it is positive. They change the electron, the energy involved to remove that electron is positively charged. You can see sodium in the gaseous state, you lose 1 electron, and this is the energy of that is involved for the ionization energy. The electron affinity is also negatively charged, by collection of one electron, and you can see chlorine becomes negatively charged, and it has this delta E. So attraction between the unlike charges draw ions together. So when you now have a positive charge and a negative charge, opposites attract. So the negative of sodium, positive charged sodium, looking for negatively charged chlorine. Similarly, positively charged calcium, looking for negatively charged chlorine. And that is where bond will be formed. And when this attraction occurs, there will be energy released, the energy of formation, which is an exothermic energy. So when sodium reacts with chlorine, it now gives you sodium chloride, whereby an electron is transferred from sodium to chlorine. So the ionic compounds, they do not contain discrete molecules, but they are, so the compound that is formed now is called an ionic compound. So that's why it is called ionic bond. And they contain ordered arrays of positive and negative ions. So the positive ions and negative ions are ordered in an array. And that is the formula unit will give us the combining ratio. One atom of chlorine will reacting with one atom of sodium. And similarly for this, the combining ratio of this is one atom of calcium, as you can see, and two atoms of chlorine. Each chlorine atom collecting one electron that they need to fill their shell. So the number of electrons that is lost by metal atoms is usually the number gained by the non-metal, so that at the end of the day, you have a neutral compound. So if sodium gains one electron, chlorine will collect one electron, and you can see that they have a neutral compound. So other examples, we have magnesium chloride. Magnesium is also in group 2, having 2 valence electrons. Chlorine has 7 valence electrons. So chlorine needs 1. So when chlorine collects 1 valence electron and it becomes 288, remember originally chlorine is 287. It collects 1 electron, becomes 288. But magnesium is still having an extra one. So the extra electron of magnesium is given or transferred to the second chlorine, and you now have magnesium chloride, MgCl2. So what are the properties of ionic or electrovalent bond? The ionic bond is formed due to the Coulombic attraction between positive and negative charged ions. Ionic bond is non-directional, that is, the strength of the interaction between the two ions depend upon distance, but not on the direction. So it's non-directional. And the ionic bond can be broken when the substance is dissolved in a polar solvent like water. So let's say that's why your example, your sodium chloride salt, if you put a full spoon of salt in water, it will dissolve, because the ionic bond can be broken in a polar solvent like water or polar organic solvents. Once it is not polar, it will not be broken. So it can be broken in the polar solvent, and that substance would dissolve. Or when the substance is melted. So at high temperature, you can see that when you pour hot water, it will melt instantaneously, because ionic bonds break when it is melted or it dissolves in polar solvent. So what are the factors that influence the formation of ionic bond? Low ionization enthalpy of the metallic ion, of the metallic element which forms the cation. So low ionization enthalpy, large electron affinity of the non-metal which forms the anion. Then we have the large lattice energy, that is the smaller size and higher charge of the ions. So properties of compounds, like we said, they have high melting and high boiling points, because look at sodium, for example, the ions are fixed in place. When you see the positively charged, the purple balls are the sodium atoms, while the green balls are the chlorine atoms, positive and negative charges. So when they are heated, remember we said they are in layers, but when heat is applied, the ions begin to glide upon one another and begin to move. So they have very high boiling points and high melting points. And also they are good conductors of electricity when molten, but non-conductors when solid. So when salt is your sodium chloride you add, you put, it will conduct electricity when it is in a molten form. Will not conduct electricity when it is in a molten form, but when they are in molten form, they after dissolving in water, the ions can migrate or move about in the water and create an electric current. But as it is, it will not be able to conduct electricity because the ions are fused together. But at higher temperature, they can slide or glide over one another, and they're able to conduct electricity. Another factor is that they are readily soluble in water and in polar solvents. So they are readily soluble in water and in polar solvents. So if you have water now, this is a water molecule. The sodium ion will get attracted to the negative ends of water, while the negative chlorine atom will be attracted towards the hydrogen, which is the positively charged. So they're easily soluble in polar solvents because of the polarity of water molecules, and they will be dissolved. Then the crystals of ionic solids are hard and brittle. Like for sodium chloride, the crystals are usually very hard and brittle to break. So we have a question: which of the following compounds would you expect to be ionic? N2O, NaO2, CaCl2, SF4. So we have examples now. So which one will be ionic? Remember that ionic compound is between metal and non-metal. So the two of them are non-metal, ionic bond will not form. But if one is metal and the other is non-metal, you expect ionic bonds to be formed. And also, I'll give you this in the slide to complete the table and fill the formula of the ionic compounds that will be formed by these pairs of cations and anions. So this will be your assignment to practice. So we have also to predict whether these elements would undergo ionic bonding based on their atomic numbers. So what you need to do is now that you write the electronic configuration of these elements and look at the valence electrons. If it has one or two, if one of them has 1 or 2 or 3 valence electrons and the other one has 6 or 7 valence electrons, you can be sure that there can be an ionic bond between the pair of atoms. Then the next question asks that which of these pairs will have a higher melting and boiling point. You know that the one that has the higher melting point and boiling points are those that can undergo ionic bonding or electrovalent bond. And that has to do with it between a metal and a non-metal. We have to look at the electronegativity, the ionization energy, as well as the electron affinity to know which one has the higher melting point and the higher boiling point. And another question is to identify which of the following compounds will easily conduct electricity in solution or in molten states. This also you need to know that it must be ionic compound. Anyone that is not ionic there will not be able to conduct electricity in molten form. So this brings us to the end of the class. So I will unmute you. And if you have any question, you can ask your question now. Abdul Yunusa, you have a question? So just unmute yourself.
Please, ma, is there a formula for determining the amount of electron that each shell can carry?
I can't hear you.
I said, is there any formula to determine the amount of electron that each shell can carry?
Yeah, you have it already that your first shell has your s orbital has 2 maximum, the p has maximum of 6, and the first shell can hold 2 electrons. Then the next shell will hold 8 electrons, and it goes on and on like that. You were taught this before. There's no formula to that. There's a principle that the atoms follow. Yes, Cynthia.
Hello.
Cynthia.
Good morning, ma. Ma, please, how does high lattice energy affect the formation of ionic compounds? And also the statement that ionic compounds are both hard and brittle. I don't understand.
It's because they form crystals. If you look at the slide that was shared, they form crystals, and because they form crystals, they arrange in crystal. The arrangement of the ions let me go back to that. You see now that they form. Let me go back. The positive and the negative ions are arranged in layers. They are arranged in layers, and it depends on the size and the charge of the ions. For example, the size of sodium ion, because sodium has atomic number of 11, the size is different from potassium that has 19. Then the for the negatively charged ones, different from iodine or chlorine. So the size of the crystal is dependent on the size of the ions that form the crystal. If you are not talking, please mute yourself. Yes, who else has a question? Adebayo David.
Ma'am, my question is that are we to submit the assignment or just
No, do it,
just
practice the assignment, the questions, practice them. And in the exam, even if you are not submitting now, in the exam, you submit them if they are asked in the exam.
Okay, ma'am.
Your own interest,
Thank you, ma'am.
Practice this. In case it comes out in the exam, you know the answer. Ibiabuchi,
okay,
I have a question. Yes, I wanted to ask aluminium. Yes, ma. Aluminium.
Yes.
Ma, is aluminium a metalloid or a non-metal?
Aluminium has 3 valence electrons. So in this case, it can also transfer the 3 electrons to become an object.
Thank you, ma.
When it is reacting with a non-metal.
Okay, ma.
Olani Iboluwatife Sarah.
Good morning, ma. Hello, good morning, ma. You were speaking to us how to.
I can't hear you. If you're not talking, please mute yourself.
You were explaining to us how to get the boiling point and melting point. I did not really get that, please.
How to get the boiling points.
And melting
I didn't
point.
teach you how to get the boiling point. I only said that ionic compounds have high melting points and high boiling points. And that is as a result of the enthalpy. We talked about that before. When we look at the enthalpy, that they need energy to remove an electron is exothermic, and you see the to add electron to the non-metal, and that is what gives rise to that. And let me go back to that slide. So you see here now that for group 1 elements, they have the electron, the energy that is required to remove that 1 valence electron is the ionization energy, and metals have low ionization energy, while non-metals have high ionization energy. And in terms of electron affinity, the energy that is released when an electron is added in the gaseous state to a non-metal is usually very high. And you can see in this slide. So they are non-metal. When the non-metal and the metal come together to form a compound, it's usually very energetic, and the high energy there gives rise to the high boiling point and the high melting point. Yes, who again has a question, class? So I think we can conveniently end class. And so, like I explained before, your lecture will continue on Wednesday on the timetable, but you check on the LMS to know the group you belong to and join that group. There's a maximum capacity for Zoom for students, and that is why we have to quickly go to our groups by Wednesday to know where we belong. Thank you very much and have a nice day.
Ma, please, what of those that can't see the LMS yet?
That is not my problem. We went on LMS in the first semester. You're on LMS in first semester, so you can always get your go on the LMS for you to have to see your lecture schedule. So everybody, if you're a registered student, should be able to access the LMS.
Yes, I'm registered for the course, but I can't see the course on my LMS.
You can't see the course on your LMS.
No, I can't.
Then you have to visit the site here. Not the one that
Okay, ma. All right, ma. Thank you, ma.
Okay, who else is asking questions? The time for the class.
Have a
Who else
great
is
day, ma.
asking questions?
Please, ma, we to write our name, matric number, and course that we're doing.
Nobody will be able to read that. And because for today, because the class cannot take everybody, because the class cannot take all of us, I won't penalize those that could not join. So you can't take attendance. By the time you are broken down with your groups, you should be able to, maybe attendance will be taken at your various group levels, but we can't penalize those that could not join today because we exceeded, the number exceeded the maximum that LMS can take. All right. Who is asking the question again?
Hello, ma.